In this video, we'll continue our discussion of evaluating limits algebraically, and this time we have a more unique type of problem, and I'll call it expand and simplify. What you might notice about this problem is that we not only have x's, but we also have delta x's, which are change in x. And so it's like having two variables. It could, for all intents and purposes, delta x is just operating as another variable here. But what this is doing is setting us up for evaluating derivatives or finding derivatives using the limit process. And a derivative is just a rate of change. And so this technique will be used later on, and we're setting the stage for that by just learning how to do the algebraic manipulation before we get into the calculus concepts in addition to that. Alright, so you can see here that we have our list over on the right side. Direct substitution, if we plug in delta x equals 0, we're going to get x squared minus x squared, which is 0 in the numerator and 0 in the denominator. So once again, we have an indeterminate form, and we have to go on to find another strategy. Factor and cancel. Well, there's nothing really to factor. The numerator is already factored. We have that squared binomial there. So we can't really factor anything more from that. There's no radicals to rationalize. There are no complex fractions to simplify. But we can expand out the expression x plus delta x squared. And so that's where we'll go with this now. So we have limit as x approaches 0. And when we expand out x plus delta x, we get x squared plus 2x delta x plus delta x, and I'll just put that in parentheses, quantity squared minus x squared. So to multiply out a squared binomial, it's first term squared, then multiply the two terms, x delta x, and double it, so it's 2x delta x, and square the second term, add it. And our denominator is delta x. So once we simplify that out, then you can see that at least something happens. The x squares disappear, they zero out, and we'll rewrite limit as x approaches 0 of 2x delta x plus delta x quantity squared over delta x. You might see that now we can factor out a quantity delta x. That leaves us 2x plus delta x in the numerator, delta x in the denominator. Now we can cancel the delta x's, leaving us with limit as x approaches 0 of delta x, sorry, these should all be delta x's approaching 0. Delta x approaching 0. 2x plus delta x. We can now plug in delta x equals 0, and we end up with 2x. Which, in this case, what we've really done here, although they don't say it yet, is we have found the derivative of y equals x squared. We've found the rate of change of y equals x squared, and it's dependent on the x value. It's 2 times whatever the x value is for that particular 2 times whatever the particular x value is. Now I've put out some more examples similar to this one that are in this particular problem set. The one that we've done is not the simplest one, but it's certainly not the most complicated one. So you can see problem 61 and 62, although conceptually are the same or similar to the one we've just done, algebraically there's a lot more going on there, and so it's a bit more complex. You just have to do them very carefully, watching out for your signs and etc. Alright, so that's going to do it for this problem, but I think you can get the basic idea and go ahead to work on the other ones in this set, similar ones in this set.